for which the formula evaluates to be true. If that is so, we say that the formula is satisfiable. Otherwise, we say the formula is not satisfiable, right? And we stopped at working on encoding a particular problem into a satisfiability problem. The first example that we started with was coloring the elements of a Pythagorean triple, right? And there are infinite number of Pythagorean triples. And the task in hand is that we need to partition the set of integers into two sets such that no set contains a Pythagorean triple. And we started to talk about a different variation of the same problem. And the problem goes like this. So you have this Pythagorean triple and you can paint. Yes, hello.
Excuse me, sir. Did you share the slides? Because slides are
I
not.
don't know. I did that. Uh,
No, no, sir. Slides are
okay,
not.
okay, okay, okay. Sorry, sorry. Is it visible now?
Yes, sir. Now
Yeah,
it's
thank you.
visible.
Thank you. So we were talking about these problem, right? So this problem we have already talked about, and we are trying to talk about a different variation of the classifying this Pythagorean triple or partitioning this Pythagorean triple. So this is your triple A, B, and C, and you can paint the individual elements of this triple using either of the two colors, either red or blue, right? Now, you cannot color all of them with the same color. So it is not like you'll be assigning red, red, red to ABC. You cannot really do that, right? So what you can do, you can paint A and B with red and say C with green. That is allowed, right? Now, the question is whether we can do it for all the Pythagorean triples, right? And it was kind of discovered that we can do this up to, so we can divide a set of integers up to say 7, 8 to 4. Now, as soon as we encounter 7, 8 to 5, then the whole property that we can partition this set of triples into two classes or two sets, that breaks down. So it is not possible beyond 7824. So until 7824, we can color the integers in such a way, but as we encounter 7825, we cannot really do that. And actually, the solution to this problem was demonstrated recently in 2016, and there was a paper published in Nature, and the proof was obtained by a SAT solver. And the point that is very astonishing is that the proof that amounted to say 200 terabytes. So if you want to store the proof of this particular problem, whether you can do that or not. So we'll come to the SAT encoding of this problem. So basically what we're trying to see whether we can partition the set of integers in this way or not, right? So the proof was obtained and this was kind of 200 terabytes. And this is the largest math proof ever, right? You see the power of SAT solver. So I'm just trying to illustrate how powerful is this SAT solver. And of course, we'll be doing an encoding, SAT encoding on this problem. So I'm not going to run this. So this was there was a prize money associated with this. And this particular person, Margin Well, who received this prize. Uh, Now the next task. So this video is from Number File. So there is a very interesting channel in YouTube which is Number File, and this has got a very interesting problem starting from number theory and other things. So if you have some time, you may like to visit this. And if you talk about this particular problem, this has been well illustrated in this embedded video. You can have a look at this. Now let us try to map this problem into a SAT problem. How do we do that? So basically for each integer I, we are defining one Boolean variable. So you have to come up with a Boolean formula at the end, right? And we set xi to 1 if we assign, say, blue color to say color integer I, right? So we assign xi to be value 1 if we assign say blue color to integer I. else we assign our value to be 0. So basically for each variable, either we are assigning the value to be true or false. So that means it's a Boolean variable. Now for each triple, a square plus b square equal to c square, we need to define we need to present a clause like this. So first clause is xa or xb or xc, and the second clause is xa bar, xb bar, and xc bar. So you can check whether this is happening or not. So let's say we color abc with all red, right? Now this will become true. So the first clause will become true. What about second clause? Second clause will become false, and as a result, the whole formula will become false, right? Now let's say we color say AB with red and C with say blue, right? So we have a true value here if we do that. So basically what we are doing, red, red, and blue. And here we are getting a truth value, true. And finally, this is evaluated to be true. So this particular formula F is encoding the fact that all these three variables, they cannot be assigned the same color at the same time, right? This is a problem instance where we have set n to be 55. So what we are doing really, uh, we are looking at the set where we have the integer from 1 to 55, and we are accumulating all the Pythagorean triples. So for example, x3, x4, x5 is a Pythagorean triple. So that means we have to insert this formula in the final formula. So x3 or x4 or x5 and x3 bar, x4 bar, x5 bar. And this 5, 12, 13 is another Pythagorean triple, and we need to include the same type of formula here. And we did till the Pythagorean triple, last Pythagorean triple up to 55, that is 33, 44, 55. Now see, we can encode this entire problem into a propositional formula, as you can see here. Now what we need to come up with, we need to come up with the assignment of this, say, x3, x4, x5, x3, x4, x5 until, say, x33, x44, x55 in such a way that this becomes satisfiable, right? And it has been observed that we can have a satisfiable assignment up till 7, 8 to 4. But as long as, or as soon as we encounter this, this whole formula becomes unsatisfied. So this is how we can encode a problem into a SAT problem. Right? Talk about graph coloring, which we have discussed in the last module. So this is a very special graph, which we call as McGregor graph, which is a planar graph, and as well as it is having 110 nodes in it. I think I have discussed what is a planar graph. So you can draw the edges between them without crossing any two edges crossing, right? So that is in a nutshell what is a planar graph, right? Now the hypothesis was that it cannot be colored with less than 5 colors. And that brings us to the problem of a graph coloring problem, and this is specifically called K coloring problem. What is the problem? The problem is that you can color a graph using at most K color. If you can do that, then it is called a K coloring problem, right? Now, the first thing that we need to ask, if we want to have a SAT encoding for this kind of problem, is what would be my variables? And of course, the variable should be Boolean variables, right? So what we can do, for each node Vi, what are the color options? We can have color options, say 1, 2 to K, if we have K colors, right? Now what we can do, we can paint this node using one of these colors, right? Now we define a variable Vj, which means which we will set to true if this V node gets color J. Then we set it to be true, otherwise we set it to be false. So how many variables in total we will be having in a graph having say V nodes? So you'll be having this K multiply V number of Boolean variables, right? Now let us focus on what would be our clauses, right? So the first thing that we need to ensure that every node gets a color. And what basically we will be doing for every node V, we need to assert this clause that either of this assignment V1 or V2 or VK, that will be true, right? That is understandable. Now, what is the next clause? And that the next clause relates to the fact that no two adjacent nodes will be having same color, right? So we are taking one edge, UV belongs to capital E is the set of edges. And we are inserting this particular clause, which says UJ bar or VJ bar. And what does that mean? Let's say we assign color J to U, right? So that means UJ becomes true, right? Now, can we assign the same color? And as UJ becomes true, UJ bar becomes false, right? And in order to make this clause to be true, what we need to do, we need to make this VJ to be true because this has become false. Now, how do we make this to be true? We can make this to be true if we make this assignment false to VJ. And what does that mean? That means that we cannot assign, we are not assigning the jth color to the variable, the node V, right? And you see that is exactly what we are trying to impose, that no two adjacent nodes will be having the same color, right? And we'll be doing the same for all the nodes and all the edges. So let us see that this is the graph that we are interested in. So what are the variables? The variables are U, V, X, W, X, Y. And let us assume that we want to see whether we can paint this entire graph with three colors, right? So what would be our variables? The variables would be U1, U2, E3, V1, V2, V3, and finally X1, Y1, Y2, Y3. So for every node, we are having three such instances, right? And what would be clauses? The first clause concerns every node gets a color, and we can represent with these clause, which we have discussed earlier. And the adjacent nodes will have different color, right? So for that, for every pair of nodes which are connected via an edge, we need to assert this clause. And I hope this is understandable given the description in the earlier slide, right? So again, we see that we can encode a graph coloring problem which we have solved using CSP in a satisfiability domain. And finally, what we get to find, we need to find a satisfiable assignment of all the variables that we have listed down in our problem encoding, right? So with this, so there might be many other examples which we can work on and try to encode them as a SAT problem. Now, after encoding, the next step is to design our SAT solvers, right? Uh, Now, as I have mentioned earlier, this is the approach that we'll be taking. So the first approach that we'll be taking, as we are trying to find out the satisfiability of our propositional formula, we know that we discuss some inference rules, right? We'll first check whether we can use some inference rules that are defined to check whether a particular formula is satisfiable or not. And we'll be taking that kind of approach to design our algorithm. The second kind of approach we'll be taking whether we can map the SAT problem to a SAT search problem, SAT to search. So this will be our next exploration. And the third exploration we'll be doing to combine this inference with search. So these are the three things we'll be doing. And one thing that I like to mention here, that all the algorithms that we'll be talking about, they are all complete algorithms. So though there are algorithms which are incomplete, we'll not be discussing them. Maybe I'll give you some pointers. If you are interested, you can explore them. Right. So till this point, are there any queries or doubts? Let us move on. So the first case, the inference-based algorithm. So, but before that, let us try to review something which we have already done and which will be useful in designing the algorithms, and we'll be defining certain things which we'll need to devise the algorithms, right? Now, what is the first thing that comes into mind while you try to prove a propositional formula? So can anybody tell me? Can anybody help me with that? So what is the first thing that comes into mind while we talk about uh, proving a propositional formula? Just try to go back to your logic classes and respond. I do really expect an answer at this point. This is very basic. Okay, let me know whether you ever heard of the term, say, resolution technique.
Yes, sir.
Okay, so as we talk about resolution technique, so let me write down something and tell me what would be the output. So A1 or A2, say, or X, or say A3 or A4. So this is one statement that is there in your knowledge base, and the other statement is B1 or B2, or say not of X, or say B3 or B4. So if we apply resolution on these two, what will I infer? Can any one of you tell me?
A1 or A2
A1 or A2,
or A3 or A4
A4.
or B1 or B2 or B3 or
Good. So this is the thing that we'll be inferring, right? So this is basically we are doing by applying this resolution. And actually this resolution is at the core of the satisfiability solvers, right? And that's why we will try to define it a bit more formally, right? So let's say we have a Boolean variable P. So P is a someone's mic is on. Dipan, can you please put your mic off? Yeah, thank you. So you have this, this is a Boolean variable. Let us assume that, right? And by delta, we will always mean going forward, it is a CNF clauses. So this is a set of CNF clauses. And it at this point, so this is in general, I'm talking that this will be our knowledge base in the examples that we'll be talking about later, right? Now, at this point, let us assume that this delta is containing two clauses. One is CI and CJ, right? And also let us assume that P belongs to CI and not of P belongs to CJ. So what do you mean by that? P appears in a positive form in the clause CI and negation P or P appears in a negated form in clause Cj. Now, if we apply resolution, what would be the derived clause? So we are just reviewing this, but in a different way. So let me just put it, then you can say whether I'm writing the thing in an appropriate manner or not. So as an outcome, we'll be having something like this. This or Cj. Is this correct?
Yes, sir.
So basically, I'm writing this exactly this thing in a different way. And if we are doing this, we are doing the resolution on a particular variable, which is P, right? And this is what the outcome that we are getting, we call it as a P resolvent. And this is a definition that we will be using later. And you need to kind of understand this and try to keep in your memory, right? So we are kind of performing the resolution on a particular variable, and as an outcome, we are getting the derived clause, and this derived clause is called the P resolvent if we are doing this resolution on variable P, right? Now, a quick example for this would be like, so let's say we have got something like A, B, or negation C. So whenever we are writing the things in this form, we'll be assuming that these are in their disjunctive form. And so this comma, the usage of comma will be overloaded. So what do we mean by that? So this is also appearing in disjunctive form, but these two, they are appearing in a conjunctive form. So this is what we need to agree with. So this is the kind of convention that we are going with, right? Now, if we try to do a resolution over the variable B, so the output clause will be, as an output clause, will be obtaining A, negation C, and D. And this is something that we are getting as B resolvent. And we'll see that the algorithms that we'll be deriving is basically we are applying this resolution rule in some way, right? Now, as we apply these resolution rules, maybe iteratively, we might encounter a state where we derive an empty clause. So let's say we have something like this. So we have, say, B and say not B. And there may be something here, say A, not C, D, something like this, right? Now, we can perform a B resolution here. As we perform a B resolution, what we'll be getting? One empty clause, and we have this. So what is the state of the knowledge base now? We have a clause which is empty, and that means we have an unsatisfaction here, non-satisfaction here, and this is what we do not know. So this evaluates to be false, and this, I don't know what it will evaluate to. But finally, what the entire thing will evaluate to? The entire thing will evaluate to be false. So this is what we mean by deriving an empty clause. So after doing this resolution, we are deriving an empty clause, and that will lead to something we are interested in, that in the form of unsatisfiability. So in this case, we'll be getting a unsatisfiability, right? So we'll be going back to this later. Let us try to see other things about resolution. So the first statement that I can make on resolution is that resolution is sound. Of course, we know that, right? And I hope that you understand the definition of soundness and completeness, right? So resolution is sound. This is, we all know. But also we know that this is incomplete. What do we mean by that? That we are not, so I'm focusing on this incomplete part. We are not guaranteed to derive every clause that is implied by a given knowledge base or given CNN. So I hope you agree with that, right? So if I say that an algorithm is incomplete, so that means we are not guaranteed to derive every clause that is implied by the knowledge base, right? So that is a, yeah.
Sir, for propositional logic, this was complete, right? Because you had a finite set of inferences.
No, actually, it can prove that this resolution is sound, but it is not it is not complete. So I understand what you are trying to mean. I'm coming to that point. But one can prove that resolution is refutation complete. So these are two different things. So what do we mean by refutation complete? So we are guaranteed to derive an empty clause if the knowledge base is unsatisfiable. So let me write it down. We are guaranteed to derive an empty clause if delta is unsatisfiable. Right. So actually this observation is the basis for this resolution based complete algorithms that we'll be talking about. Based complete SAT solvers. Right. So what we will be doing? We'll keep on applying this resolution rule until, so there would be two possibilities. So what we do, we keep on applying this resolution rule repeatedly, and there might be two cases, two outcomes. One is you encounter an empty clause. So that will say that your knowledge base is unsatisfiable, or you get into a situation where no more application of resolution rule is possible. And yet you did not encounter any inconsistency. And that will bring us to the outcome of satisfiability. So these are the kind of basic steps that we'll be doing. So let us have a quick example for this, right? So let us work with a very small knowledge base. So in our knowledge base, we have, say, not PR. So this is one clause. The second clause is, say, not QR. The third clause is, say, not of R, and fourth clause is, say, PQ. So these are the clauses that have been there in the knowledge base. So this is our data, right? Now what we can do, we can say apply resolution here on R to derive not of P. Hello. So here we can get not of P if we apply resolution over 1 and 3 clause, right? Now similarly, we can apply resolution over this 2 and 3 to get not of Q. And maybe we can apply, say, 4 and 5. So we can check, say, 4 and 5. And we can derive what? We can derive Q. And finally, with 6 and 7, we can derive one empty clause. And that is where we are getting unsatisfiability. Right. But see, your knowledge base will not be that simple and that easy. There might be huge number of variables. Actually, there is a competition that held in every 2 years. And there are different challenge problems that are floated. And in some problems, you might be having millions of variables. And there might be thousands of clauses which we need to take into account. Now, let us go with other definitions. I guess you understand what we mean by unit resolution. So what is a unit resolution? Where at least one of the resolved clauses has only one literal, right? So let us take a quick example, say P and Q, and you have something, say not of one. So here you can see that we have one clause which is involving one literal, right? So that's why this kind of resolution is called a unit resolution. And we'll see that unit resolution will be playing a very important role in devising efficient solvers. So this is very important to us. Now we define something called conditioning. So what we are really doing, so we have a knowledge base and we have a set of literals, right? We have a set of literals and or variables. Now, for each variable, we are trying to find a truth assignment, either true or false, right? So we are making a decision whether to assign true or false to this variable. And if you assign the value true, then your knowledge base becomes revised to be a different one. And if you assign false, your knowledge base becomes a different one. And what if we choose a value, a particular value to the variable and try to reassess the state of the knowledge base, and we will be coming up with an updated knowledge base, and that process is called conditioning, right? So conditioning of delta over literal L. What does that mean? You replace every occurrence of literal L in delta by true. So you replace occurrence of, say, L in delta by true and occurrence of negated L in delta by false. And whatever you will be getting out of this, that is what we call as conditioning of the delta over L. And we represent that as delta L. And mathematically, we can represent it like, say, alpha minus, I'll be explaining this later, L, such that alpha belongs to delta and L does not belong to alpha. So let us not look at this. So let us try to assess what are the kind of effects that we'll be having if we try to condition this delta over L. So there are basically the existing clauses in delta can be partitioned into three sets. The first set is your L, whatever you're selecting here, this may belong to alpha. So this can be one class, right? Now try to look at what will happen if L belongs to alpha. Can anybody guess? So what is your alpha? Alpha is a, yeah.
It will be true.
So this alpha will always be true, right? So if alpha becomes always true, then there is no point of keeping that in the knowledge base, because I do not have to check it further, right? And what decision we can make for this updated delta? This alpha does not appear in delta L. So that's why we are saying that L does not belong to alpha. So if L belongs to alpha, then we'll be trying to include that alpha, but in a different form, right? Now let us check the other case, that L, negated L belongs to alpha. So again, what will happen?
L should be removed, because if it is there, then it will be or with 0. It will remain the same.
Right. So your alpha is something like, say, A or not of L or say C, something like this. Now, if this belongs to the kind of alpha, and we are setting L to be true, and what will this evaluate to? This will evaluate to false. And if that is so, the truth value of alpha will depend on only A and C. We do not need to consider this negated L. So what we'll be doing? We'll be including alpha minus, or so negated L in the updated in delta L, right? The third case is that neither L nor negated L belong to alpha. So in that case, it is very trivial to know that alpha should appear in this conditioned knowledge base, right? I hope this part is clear. So I think it will be more clear if we take a very quick example, right? So let's say our delta is something like this. A, B, negated C. Then you have something like not of A, D, and you have something like B, C, and D, right? Now let us try to condition it over C. So you can tell me what will be delta C here? Just have a look at it and tell me based on the prior discussion.
AB,
AB,
comma, not AD.
not AD.
The last one will not be there.
Last one will not be there. So I think others will agree with him, right? Now again, we can do conditioning over not C. If we do that, what we will get, again, not AD will be there. The first one will be gone. And we'll be having the second one removing this, the third one removing this C, right? Now this is the example of conditioning over a single variable. Now we can do the conditioning over multiple literals. So we can do conditioning on multiple literals, right? So let's say we have conditioned this on C. Now we can condition this, the updated knowledge base, on A also, right? If we do that, what we will get as an output, say D, right? Now then, if we do our conditioning over, say, C, A, and not of D, what we will be getting? So this will become empty, right? So let us write this down, this empty to be denoted, say, by this phi, right? So this is one case, and this case points out to the case that we are getting a not satisfaction case, so unsat case. Now let us do this conditioning in a different way. So let us condition this knowledge base with first C, and if we do that, what will be, we have already this, right? And then let us condition this over say D. So as an outcome, what we'll be getting, this becomes true, this becomes true. So true becomes true. So we do not have any other clauses left. All have become evaluated to be true. And basically we'll be having a empty set. So this difference that I really want you to notice. So this is a kind of case of satisfiability. So these two, phi and this phi inside a set, these two are different. So this is the case of satisfiability and this is the case of unsatisfiability. This is required while we are developing the algorithms further, right? I hope this part is clear, right? Now we have all the ingredients to talk about our first algorithm, which is our inference-based algorithm. And that algorithm is called DP algorithm. And it is named after two scientists. One is Davis, the other is Putnam. So in this lecture, I will not be writing down the formal algorithm. You can visit the video lecture that I have shared with you earlier, but I'll just try to do a dry run of the algorithm and tell you the basic things that we are going to do in that algorithm, right? So here we are using a concept what we call as directed resolution, which is nothing but to apply resolution rule repeatedly. Right. But we want to do it in a very structured way. And for this to impose a structure in our method, what we do? So if you go back to the earlier example, we are applying, we are deriving different P resolvents. So here we have first derived C resolvent. And on that, we have tried to derive, say, A resolvent. And then finally, we have worked on D resolvent. Right. Now, try to look at the kind of method that I'm trying to illustrate. So we are picking up a literal or a variable and then trying to perform a resolution and then going to the other variable or literal. So can you do that? Well, we could have done this A resolution first and then say C resolution. We'll have similar kind of output. So that I want you to check. My proposition is that we can work with any ordering. The outcome will be finally the same. But depending on the ordering of the variable, we'll see later, we can find our solution pretty early in some cases, and in some cases, we can find the solution in a delayed manner. But the point that I'm trying to make here that we are taking each variable and trying to apply the resolution on that variable. And that brings us to a method which we call as bucket elimination. We are treating every variable as a bucket. And we are putting the clauses and we are picking up the clauses from the knowledge base delta and putting them into the respective buckets. And what is the benefit of doing that? There you know that I know that for a given variable, what are the clauses that are involved with this variable so that I can apply, say, resolution on that particular variable. So what we'll be doing first will be creating bucket for each variable. Each variable. Then we will have one pre-decided ordering. Ordering of variables. And let us name this to be, say, pi. Pi is the ordering of the variable. And using this ordering, we will fill the buckets. Right? Now, how do we fill the buckets? So we'll pick up a clause from delta and we will add this, add alpha to P, and we'll do that from top. So I'll just take the example and try to illustrate what we mean by from top, right? Such that P belongs to alpha. And this belongingness can be in any form. It might be either in positive form or it might be in negative form. This might be any. So in any way, this variable is appearing in alpha. If it is appearing in alpha, this alpha will be put in the bucket P, right? So that's how we'll be working. So let us take an example and try to see how this bucket elimination works. So the example goes like this. So this is bucket elimination example. So our delta is something like this, not A, B. Then you have, say, not of AC. Then you have not BD, something like not C, not D. And finally, we have AC, A negative CE. So what we need a pre-decided variable ordering pi. So pi is, let us assume, say, C, B, A, D, E. We could have chosen any such pi. So your algorithm, what are the inputs? The inputs are this delta and pi, right? Now, the first thing that we'll be doing is we'll be creating buckets for each variable. So C is a variable, B is a variable, A is a variable, D is a variable, E is a variable. Now, the next task is to pick up every clause and try to see which bucket it should fit in. So first tell me, if you choose this clause, in which bucket it should belong to. So of course it should belong to this B bucket. So we are trying to probe from the top, and this is the first place where we have a variable that belongs to this clause. So that's where putting this clause in this bucket, right? Now AC, where should I put it? So we should put it here. Now you have got BD, where should I put it? We should put it here. Now C, not D. Of course, you should put it here. Finally, this, and this should also find a place here. Now we have constructed our bucket. So the next thing is to apply the directed resolution, perform the directed resolution. Now, if we perform directed resolution, we first be trying C resolution, right? So if we try C resolution, let us check these two clauses. So we have got all the conditions satisfied to apply C resolution. And if we apply that, what we will be obtaining? We will be obtaining not of A, not of D, right? Where should I put it? Of course, we should put it under A. And as this is an outcome of the resolution, we'll be putting it in this part. So not of A, not of D, right? Now, let us check these two pair, this pair. This is also a candidate for C resolution. Now, if you resolve this, what we will be obtaining? We will be obtaining not of A, E. Should we put it somewhere? What do you say? Should we keep it somewhere? Or if that is so, why should we keep it? Any idea?
Sir, it can be further simplified also.
So if we simplify this, what will it evaluate to?
E.
Will it be evaluated to E or something else? So basically,
true, right?
It will be evaluated to true, right?
Yes, sir.
So as it is being evaluated to be true, I really don't care about it. So I'll not be putting in it anywhere, right? Now we are left with another. So this and this, we can apply B resolution here to get not of A, D. And you know that we can put it here, not of A, D. Now what should we do? Any idea? Can I apply D resolution here?
Yes, sir.
Just go back to the algorithm and check. So for every bucket, we are applying the resolution on that variable itself. So you are just applying the resolution. Here we will be applying C resolution. Here we will be applying only B resolution. And here we will be applying only A resolution. So we will not be applying D resolution here, right? So this is as per the DP algorithm, right? And finally, we are in a situation. So did we get any unsatisfiability? No, we did not get any unsatisfiability. Do we have any new rule application as per DP algorithm? No, right? So basically this will give us the case of satisfiability. This knowledge base will be satisfiable or consistent. Now one may argue that, well, if we have a different ordering, like say EA, oh, just give me a second. The entire thing is gone. Okay. So if we have an ordering like this, say pi equal to AE, A, B, C, D. So first question is, will we have the same outcome? The second thing is the number of steps. Does it depend on pi? So these are the two questions. I think I leave these to you to explore. And in the next class, we'll start talking about other ideas in this particular domain, right? So I guess I'm done for today. If you have any doubts or question at this point, I'd like to take forward. Okay, so if you do not have any questions, so let us end this meeting.